Hello everyone and welcome to another tutorial on TurboMole and its graphical user interface TmoleX. In this video, I'll walk you through the structural optimization of a periodic silicon crystal with three-dimensional periodic boundary conditions followed by band structure and cohesive energy calculations. Let's start by clicking on the New Project button. We'll name the project silicon_primitive since we'll be using a primitive cell for our calculations. It's always best to use a primitive cell for band structure calculations as it avoids band folding artifacts and saves computation time since there are fewer atoms. Next, we need to specify the geometry. Click on File, then go to import.cif file. You can download CIF files for crystals from many online databases. I already have a CIF file for the silicon primitive cell on my computer and I'll use that here. You can also find the download link in the video description. Once it loads, you will see the silicon structure appear in the viewer. You can then zoom using the scroll wheel, rotate by clicking and dragging. And under the periodic tab, you can view the unit cell parameters. In TurboMole, you can specify periodicity as 0-dimensional, 1-dimensional, 2-dimensional or 3-dimensional, so you don't need to manually add vacuum for low-dimensional systems. You can also visualize a supercell by replicating the unit cell along the X, Y and Z directions. If we replicate the cell 5 times along each direction, you'll recognize the familiar diamond structure of silicon. You can also check properties like the number of atoms, number of bonds, charge, and molecular mass. We'll leave the symmetry as C1 because periodic density functional theory calculations in TurboMole don't currently support symmetry. Click Continue to move to the Atomic Attributes tab. Here you can assign basis sets. The default is def2 sv (p), but for periodic density functional theory calculations, it's recommended to use POB basis sets, and for this tutorial we'll be using the POB dzvp rev2 basis set. Once selected, you can also see the number of basis functions for your system. Next, click on Continue to go to Molecular Attributes. Here you can set the charge and spin multiplicity. We'll use a charge of 0 and automatic multiplicity. Then click on Generate Molecular Orbitals or MOs to create the initial guess for molecular orbitals. You will see 14 doubly occupied MOs as expected for a restricted KSDFT calculation. You can even visualize the MO diagram by clicking the corresponding button. Click Continue to move to the Methods tab. We'll select DFT with periodic boundary conditions. For the functional, let's choose PBE. Let's use a grid size of M5 for slightly denser integration grids. We'll skip dispersion corrections since they are unnecessary for bulk silicon. Enable the K-point mesh and choose a 9x9x9 grid, which should be good enough for this system. We won't use smearing as silicon is a semiconductor. Under SCF convergence, let's tighten the energy convergence criterion to 10 to the power minus 8 Hartree. Leave the rest of the parameters as they are. Click Continue to go to the Start Job tab. We'll perform a geometry optimization of the ground state. That's the default option. Also enable Optimize Cell Parameters. You'll now see a brief summary of the setup, which is useful to include in publications. Click Run. Name the job cell_atomic_opt and save it. The job starts running and you can track its progress in the bottom panels. The energy convergence plot on the bottom right and gradients on the bottom left. Once the optimization finishes, you can check how well the system is converged. The results typically show up under the Convergence and Energy tabs. Here you can see that the optimization converged in about 10 cycles. If you scroll up in the output file, you'll also find the band gap in Hartrees. But note that this value may be approximate. To get an accurate band gap, it's best to use a proper band structure calculation, which we'll do next. To calculate the band structure, click Start New Job with Current Data, then go back to the Method tab. Under the K-point section, enable band structure plot. You'll now need to define the path through the high symmetry points. Click the plus icon to add lines between points. You can find the coordinates of these symmetry points using the Ripper Tools web app. I'll fast forward this part as I enter the points. Once done, click Continue. Choose Single Point Energy Calculation and click Run. We'll name this job Band Structure. After the SCF finishes, a band structure file is generated. Click on the band structure button to visualize it. You can change the units to electron volts, zoom in by dragging with the left mouse button, and focus on specific regions of interest. Here, the valence bands are shown in red and the conduction bands in blue. Zooming in, we can clearly see the valence band maximum and conduction band minimum. The plot compares well with the reference data from the Materials Project database. Finally, let's calculate the cohesive energy. It represents the energy required to separate a crystal into isolated atoms at infinite distance. The formula is given by E cohesive energy equals energy of the bulk crystal minus N times the energy of the isolated atom divided by N, where N is the number of atoms in the bulk crystal. For silicon, there are 2 atoms per unit cell, so we'll divide by 2. We already have E crystal from our optimization. Next, we'll calculate the energy of an isolated silicon atom. Create a new project and name it silicon_atom. Click on New Atom, change it from carbon to silicon and continue. Use the same basis set, that is POB-DZVP Rev2, and generate the molecular orbitals. You will see 2 unpaired electrons, which is correct for silicon's 3s2 3p2 configuration. Use the same functional PBE and grid M5 and set the convergence criteria to 10 to the power minus 8 Hartrees as before. This will be a single point energy calculation. Run the job and note the total energy. Plug it into the formula, divide by 2 and convert to electron volts. We obtain a cohesive energy of -5.1 electron volts per atom, which agrees well with experimental values. So that's it. In this tutorial, we successfully optimized the silicon crystal structure with 3D periodic boundary conditions, calculated its band structure, and also evaluated the cohesive energy using TurboMOLE and its graphical user interface TmoleX. If you found this tutorial useful, please like, share and subscribe for more such videos. Thanks for watching and see you in the next one.